Excuse me. We cannot hear. Excuse me, I think the microphone is not turned on. We can't hear anything. If someone can hear.
I can hear you, but I cannot hear the speaker.
Ah, okay. Mm.
Ok. Ah, pensavo che partisse da solo. Mi sentono adesso? Can you hear now?
Yes.
Yes. Okay. Okay, so we are here. Okay, so we were saying the corona. And then we have outside the corona, at tens of parsecs from the supermassive black hole, we have the blood-line region. So this is material still gravitationally bound to the supermassive black hole, but it's not accreted onto it, so it's not part of the accretion disk. And the optical UV radiation coming from the accretion disk that it's transmitted by the corona and not upscattered to X-ray can ionize this medium, which remits of broad optical lines has a name broad-line region. Since the ionizing front from the accretion disk is exiting in a cone, basically, outside of this ionizing cone, there are the conditions to form dust at about hundreds of parsecs from the supermassive black hole. And so here we have the dusty torus, which basically is producing the infrared emission from the AGN. And very far away from the supermassive black hole, we are now in the host galaxy, in the ISM, in the interstellar medium, and there we have the narrow line region where the emission from the accretion disk can still ionize the gas, but the line width is narrow because there is no orbital motion close to the supermassive black hole. And some AGN also possess jet, which gives the radio emission, and the jet can propagate from parsec to megaparsec from the central engine. So you can see that AGN are very complex, and hence historically there are many different classifications that you can spot from the names in this plot. But for the purpose of this talk, we are going to focus on two main classifications. The first one being radio quiet and radio loud AGN. Radio quiet AGN, like Mrk 1980, as you can tell from the name of the classification, are faint in the radio regime, and they don't have jets. Whereas radio loud AGN, for which I'm providing the example of Fornax A on the right, are bright in the radio regime, and they have these majestic radio lobes and radio jets. The reason behind this classification is very likely different accretion processes, because in radio quiet AGN, the accretion disk is radiative, so it's an optically thick and geometrically thin structure, which is accreted onto a supermassive black hole and release the energy in the form of radiation, so the optical UV. While radio loud AGN very likely possess an advective disk. This is an optically thin and geometrically thick structure, which is inefficiently accreted onto a supermassive black hole. And here the energy is released in the form of a jet of relativistic particle, which is exactly the jet. Another important classification for this talk is a type 1 versus type 2. Type 1 AGN have broad and narrow initial lines in the optical spectrum, whereas type 2 AGN only have the narrow lines. The reason behind this classification is likely different orientation. So in type 1 AGN, we have a direct view of the broad region, while in type 2 AGN, the dusty torus is along the line of sight, so they are more edge-on. Hence, the emission from the blood-line region is obscured by the dusty torus, and we only have the emission from the narrow line region, which is the host galaxy. And since the dusty torus is obscuring most of the radiation from the AGN, it's also true that type 1 AGN are typically brighter than type 2. And this leads us to the Changing-Look AGN class. This is a very peculiar class of active galactic nuclei because they have the properties of transitioning between the type 1 and type 2 phase very fast. But for very fast, I'm talking about timescale of hours, days, or decades. And keep in mind that AGN are thought to vary on timescale of 10 to the 5 years, which is basically the viscous timescale of the accretion disk. So Changing-Look AGN are an open question in AGN physics because we don't understand why they are varying so fast. And for example, here I'm providing the optical spectra of Markarian 1080. Here in blue is the one taken in 1979 and in black 1984. And so you can see that in only 5 years, the source becomes brighter and the line width becomes broader. And so it transitions between type 2 and type 1. And it seems to stay in the type 1 phase until 2015, where a new spectrum was acquired in blue. This is 2015. And you can see that again, there was a dimming of the source and a narrowing of the lines. And as I said, type 1 and type 2 also differ in the photometry. You can see the light curve of Markarian 1080 in the RU and the infrared band. And apparently, in 2010, started to become fainter and fainter and fainter, which is where we are also seeing a transition in the optical spectra. And so the people don't understand why the Changing-Look AGN exists in the first place. And Markarian 1080 is, I think, the most representative object of this class of AGN because it possesses this transition. It's shown this transition happening twice during its lifetime, and has been studied in detail because it's quite nearby. The redshift is basically 0. And you can see that many efforts have been done in the literature to try to figure it out why this Changing-Look is vary and what can we learn about the Changing-Look AGN in general by looking at this object. And actually, no one figured it out what's happening here. And so we decided to enter the discussion by introducing a novelty point, which is using the largest data volume ever assembled for this source. We decided to focus on the optical UV and X-ray bands because, as we said from the beginning, those are the region in the electromagnetic spectrum where we expect the emission from the innermost region of the AGN to come. So we want to probe the accretion disk and the corona because, given the very short time scale, whatever is causing the variability in Markarian 1080, it's likely related to those regions. And so we use the archival data from Chandra, XMMM, Swift, and Nullstar, because all of them has its strength point and allow us to study different parts of the AGN spectrum. For example, XMMM, Newton, and Swift are being used because they have the optical UV telescope on board, so we can have simultaneous optical UV and X-ray observations, so we can study the photometry and the spectral properties of the source in a broadband way, and also observe Markarian 1080 when it was in the bright and in the faint state, so when it has the broad optical lines and the narrow optical lines. And Chandra has been used because of the good spectral coverage, and Nullstar because it allows us to probe the high energy portion of the spectrum. And so by systematically analyzing this data, we are able to see what are the properties of the optical UV and X-ray emission in this source when it was in the bright and in the faint state. And we start our analysis by looking at the X-ray spectra because, so there we are probing the corona. And we started by modeling the X-ray spectra with a single power law because this is the expected morphological shape of the inverse Compton emission, with addition of the iron emission line at 6.4 keV, which is this one. And we apply this model first on all the energies above 3 keV, because here is where the emission from the corona is supposed to be dominant. And you can see that when we extrapolate them backwards, this model to soften energies, the model is underestimating the data. This means that a single source of comptonization is not enough to explain this source. And this is the first important result that we have, which differs from the literature, because we now are trying to model the emission, the X-ray emission from this source with two coronas, a hot, which is basically around the supermassive black hole, is the light blue sphere over there, and the warm corona, which is likely located in the inner part of the accretion flow, which is the green region in the top right panel. And the warm corona basically gives the soft X-ray emission, and the hot corona gives the hard X-ray emission. And you see from the spectra on the right that when we apply this dual corona model, we are able to finally reconcile the model and the data. And we can also systematically apply this model to all our X-ray spectra taken in the bright and the faint state, and see how the properties of the two coronas have varied in the transition between the bright and the faint state. And this is the result. So the hot corona basically remained unchanged because the spectral index is the same. But the normalization, which is basically a measurement of the brightness of its emission, becomes significantly lower. So this is telling us that the emission from the hot corona just becomes fainter, while the warm corona possesses the biggest variability, where the temperature decreases, the spectral index decreases, and the normalization basically goes to zero. So this is telling us that what is causing the variability in matter alternating is very likely something related to the warm corona. And since now we have two results, one is that both the coronal emission is lower, but also the warm corona is cooler. We now want to understand why is so. So the fact that the normalization is lower is a direct consequence of the optical UV radiation. So here I'm plotting all the photometric points that we have in the optical UV and X-ray bands as a function of time. And you can see that the X-ray emission is becoming lower. So the corona emission is becoming lower because it's following the trend in the optical UV. So remember that the X-ray is just the result of the reprocessing of the underlying optical UV emission. So it makes sense that if the optical UV becomes fainter, the corona emission also becomes fainter. And this is exactly what we are seeing. So the X-ray flux variability is a direct consequence of a diminished optical UV emission. So this is telling us also that something is happening at the level of the accretion disk. Now there is a way to reconcile both the cooling of the corona and the diminished optical UV flux by introducing these weird objects, which are the magnetic fields. Because doing so, we are now able to relate the warm corona temperature to the magnetic energy in the system, but also the accretion rate is now a function of the magnetic energy of the system. And now in the next slide, I'm going to show you that when we introduce the magnetic fields, now all the observational properties of Mrk alternating seems to be reasonable, let's say. So we said from the X-ray spectra, we showed that the warm corona becomes cooler. And this is because the magnetic energy is lower, because the temperature of the warm corona is directly proportional to the magnetic energy in the system. But if suddenly the magnetic energy is lower, it means that there is a physical process ongoing here that is extracting magnetic energy from the system. And we know from AGN theory that to extract magnetic energy, we need the formation of a jet. But if we have a jet which is formed, it means that the accretion disk in Mrk alternating have changed its state, because remember, Mrk alternating is a radio quiet AGN. So the disk in this AGN is slightly radiative. But now it seems that since the warm corona is cooler and the UV radiation is lower, this is telling us that the accretion disk is now no more radiative. And we think that actually the disk in Mrk alternating is now a jet SAT. So it's a jet emitting disk, standard accretion disk, which is a disk model that has been extensively used to describe X-ray binaries. And we use it for the first time to describe an AGN. And the structure is basically this, where we have an outer radiative disk, where the inner part is advective and so creates a jet. And this model basically explains all the observational properties of Mrk alternating. Because if the inner accretion flow is advective, now, as we said, a jet is formed. This jet is likely interacting with the broad-range region, wiping out the material and giving the type 1, type 2 variability. So what we think is that the formation of this jet is removing the material from the broad-range region, hence creating the disappearing of the broad lines when the source is in the faint state. But also, since now we have a jet, we have a lower magnetic energy in the system, which gives us a lower accretion rate, and a cooling of the warm corona, which is providing the X-ray spectral variability that we are seeing by analyzing the X-ray spectra. Now, since we have a lower accretion rate because the magnetic energy is lower, we also have a lower UV emission because the UV are directly proportional to the accretion rate. This makes sense because if you have a lower accretion rate, the viscous friction is lower, and so the UV is also getting lower. And this gives us the optical flux variability that we were observing while plotting all the photometric points. Now, since the UV emission is lower, we have less seed photons for the corona, and this gives us the lower X-ray emission, which explains the X-ray flux variability that we observe. Now, as a bonus, introducing magnetic fields and the interaction between the jet part of the disk and the SAT part of the disk there are models in the literature that are able to reduce the viscous timescale from 10 to the 5 to 10 years, which is exactly the timescale of the variability in Changing-Look AGN. So this is telling us that very likely this mechanism, where the inner part of the accretion disk is transitioning between advective and radiative on timescale of 10 years, can be the physical explanation of why Changing-Look AGN exists in the first place. But we want to test this model to our data, given the large data volume. Let's try to exploit as much as possible. And so we apply the spectral energy distribution fitting, so the set fitting of all our optical UV and X-ray points. And we use as a base, as an underlying model, the AGN set from Kubota and Don 2018. This model is describing the SED of a radiative disk. So now we are testing the hypothesis that the disk in Mrk 1918 is radiative in the bright and in the faint state. And when we apply this model to the bright state, we actually have a good match of the data. Now there are more data in the X-ray part. I just have to remove them because otherwise it's just a blobby black stuff there. So I just remove most of them. But the chi-square is telling us that the model agrees with the data, which is exactly what we expect, given that in the bright state, Mrk 1918 since it's a radioquiet AGN, must have a radiative disk. But when we go to the faint state, the AGN set model is a good representation of the X-ray part of the SED, which is again expected, given that not the full accretion disk has been transitioned to advective, but only the inner part. And if we focus then on the optical UV part, the model, which is the three dashed line, the dashed line on top, is overestimating the optical UV radiation. Again, this is expected given that in an advective disk, the optical UV radiation is lower because it's a different accretion process is going on, and it's not producing the optical UV emission from a radiative disk. And so the set fitting is again telling us that the accretion disk in Mrk 1918 cannot be radiative when the source is in a faint state, when the source is a type 2 AGN. If you're not convinced, then we can reach this result by looking at the accretion rate. We know that there exists a critical accretion rate, which is 2% of the Eddington accretion rate, for which an accretion disk is stable under the radiative or advective condition. So AGN, which are accreting above this 0.02, are radioquiet AGN, and AGN, which are accreting below this, are radio-loud AGN and have an advective disk. From the SED fitting, one of the parameters is accretion rate, and we can see that in the bright state, the accretion rate is above 0.02, again, confirming the fact that the disk is radiative in the bright state, while in the faint state is below 0.02, again, confirming that the disk cannot be radiative anymore. If you're still not convinced, then we can calculate the accretion rate in a model-independent way by looking at 3000 angstrom volumetric luminosity, finding that in the bright state, again, the accretion rate is above this critical value, and in the faint state is below this critical value. So we have many different evidences here that the accretion disk in Mrk 1918 is changing its state, the inner part of the accretion disk specifically. And we think that this is a general property of the Changing-Look AGN, that for this reason must be renamed as changing state AGN. Now, one question that we can ask ourselves is, okay, we have found this beautiful physical mechanism to explain the variability, but actually why then the inner accretion flow is transitioning between radiative and advective? What is triggering this variability in the first place? And we try to propose a scenario where this transition can happen. And I have to stress out that what I'm going to talk about now is a qualitative argument. So we need to test this with proper numerical simulations. It was outside the scope of our research to model this kind of process I'm describing now, but seems to be a good starting point for future studies. So the general idea is that you have a cloud or an ensemble of cloud or whatever, some material that is passing close to the accretion rate. This has been observed to happen in our galaxy, so it's reasonable to think that at some point, some material is coming close to the accretion disk, and then it starts to accrete. So what there I'm representing as a cloud is starting to accrete the material on the accretion disk. And if the accretion rate from the cloud to the disk is higher than from the disk to the supermassive black hole, then you can see that we are accumulating material over the accretion disk. And if this process is strong enough that at some point the accretion flow start to puff up, then you can see that we start to have an optically thick and geometrically thin structure, which is exactly what is the condition for an advective flow to be established. Now, there are processes that allow the accretion rate from this advective region to be higher than the accretion rate of the disk. Because there are instabilities happening at the interface between these two. There are instabilities in the temperature, in the magnetic field, so there are shocks in these regions. And so the accretion rate can suddenly increase and oversee the accretion rate in that direction. And so we have the transmission of this instability inwards, and inwards. And so now we have that the full inner accretion flow becomes advective. And as I said, this is very qualitative. We haven't done any calculation if this is possible in the first place. So if there is someone that wants to do this kind of study, I'm more than happy to provide all the data that needed, because I think it's a very nice scenario, and it's really the missing part that we needed to understand what is a Changing-Look AGN. And so here I leave you with my conclusions. So we confirmed the broadband spectral variability of Mrk 1918, and we managed to link this variability to the existing of magnetic fields that become weaker and weaker. And the weakening of the magnetic field, we think, is the result of the formation of a jet. And I have to say that recent GLBA observation has proposed that a jet is indeed present in this source. So it was nice to see that the observations are matching our expectation. And the triggering of this change of state is likely the flyby of a gas cloud close to the accretion disk. But as I said, we need simulation for this. The disappearance of the broad optical lines can be explained by the interaction between the jet and the broadening region, but we need more data to do this. And so we need to study the energetics of the jet to see if it's possible that can wipe out the broadening region. And as I said, Changing-Look might be now an outdated definition, and we could rename as changing state AGN, because it's the inner part of the accretion disk that is changing. And we think that in our interpretation is allow also to explain the rarity of the changing state AGN, because if it's true that the reason it's the almost critical accretion rate, then if you assume that there is a uniform distribution of accretion rate among all the AGN in the universe, then only a small fraction of them has an accretion rate which is close to being critical. And so every small perturbation in accretion disk can then lead to this changing of state of the accretion flow. And so this is why we think they are very rare compared to radio loud and radio quiet AGN. And since we use X-ray binaries model to explain AGN, it could be possible that this is telling us that the accretion onto a black hole, not onto a star, but onto a black hole, is universal. And it would be nice to confirm this, because then it means that we can study AGN by doing X-ray physics, and we can do X-ray physics by studying AGN. And that's it.
Questions for the speaker? Yes.
Very nice talk. I wanted to ask you, how much change, the alpha X, the slope between the X-rays and the UV? Yes.
Yes, so the alpha X, it's also telling us that X-ray are just responding to the change in the UV, in the underlying UV. Because when you compare the expected and the observed, they are basically following the trend. The blue points are following the trend of the red points. So there is a
because there are some prediction with the editor. So it's very interesting to have that for the same source. That's all.
Yes.
Thank you very much. So the key element of your interpretation is that there is a jet is taking the energy and interacting with the broadening region downside with the. But is the only way to produce a jet having a sort of other state of the accretion disk, or there are also other possibilities of creating a jet? Because Yeah, your discussion is in that there was a one-to-one relation. So you have a jet, and so you have an accretion disk that changes state, or vice versa. Is really this, or is more complicated? Or there are other possibilities.
So as far as I know, the answer is more complicated, obviously. Because I might be wrong, but I think that there are observations of a possible jet also in radioactive disk. They also have a small component, a small jet component. But here for a jet, I'm referring to a jet, like a proper jet that we see in radio louds AGN, but way smaller because the lifetime of this variation is 10 years. So obviously this jet has a lifetime of 10 years. It cannot propagate to megaparsec as we are seeing. So so the answer is it's more complicated. We need more theoretical work on this. But if we do a first order interpretation, that it's a one-to-one. So it's advective, so there is a jet. So this jet is interacting, blah, blah.
The most probable.
Yes. And actually, since we have the VLBA observation that I've seen that there is likely a jet in it.
Yeah, it was.
Then this was.
To ask you, but at the end you mentioned it.
Yes.
Nice to have also the radio.
Yes.
Is there a quantitative use you can do of the radio observation of the jet? I mean, can you relate the infrared jet power, velocity, magnetic fields to the rest of the multi-wavelength observation you just showed, or?
There is the way. This is something they want to do, because one can assume that what was observed with VLBA is indeed a jet, and so from the radio flux, I think you can infer the power of the jet, and you can see if it's enough to produce an effect on the Broadband region. And now we are trying to get ALMA data of this source, because then we have designed the observation to be sensitive enough to finally see if there is a jet or not. So we hope to get time on ALMA. But it's something I want to do at some point. I just need time for this, and since this is something that I'm doing outside of the PhD, I don't have time for this.
So, first again, about the radio jet. It is the first time that this radio jet has been observed, even if it was already observed with VLBA or VLBI resolution, this object, or it's the first VLBA resolution observation, because the presence of jets of small scale in Sierra galaxy is known since decades ago.
So this is the first.
Sorry, the
So
second question. If the radio flux increasing, because you already knew that was a radio flux, so sometimes you have.
Okay, so for the first question, I guess you were referring to this source in particular, if there was the first time.
Small scale radio jets, very small scale radio jets are known in Sierra galaxy.
Yes.
See, in a lot of not changing classical type so for this object is the first VLBI.
Yes.
So we cannot say that they are equal.
Exactly.
We say that the first time.
Exactly, and the reason is because this is a radio quiet. So in radio, it wasn't interested to observe the source. Actually, what I want to do is exactly the second part of the question, which is compare the radio fluxes, because there are VLA data of this source as part of the DLS or whatever the VLA survey. Yes, MDSS, and I want to compare the flux measured there with the flux that we can infer from the VLBA observation and see if indeed it was a rebrightening. And I want to use also the ALMA data that we are request to see if also the ALMA data are telling that there is an excess of emission at that frequencies if we assume, if we extrapolate the VLA fluxes at the ALMA frequencies. Well, it's not easy to do, but you can see if indeed that this is reasonable.
Okay, no more questions? Okay, then we can turn the speaker. And we move to the second book.